Today we are going to continue our topic of conversation, and that is matter and measurement. More specifically, again, the measurement side of it. As we go through this, we will have go through some measurements, and we're kind of getting into that point where we're getting near the end of our unit. So be ready and prepared. There are a number of things that we will need to look at and or define some of these numbers that we have. One of the numbers we need to make sure and clarify when we're making measurements is what is an exact number, what is an inexact number. Exact numbers would be looked at as your converting factors. Things that you use to convert from one thing to another. As in the examples, there are 1,000 grams in a kilogram. There's 1,000 milliliters in a liter. Okay? There is 2.54 centimeters in 1 inch. Those are exact numbers. Inexact numbers are measurements that you make in the lab. In the density lab that we did in class, you would know that your length or your width was measured in centimeters. It was not an exact number. It is inexact. So we have to maybe sometimes look at it and say inexact numbers can also be seen as lab numbers. Or maybe measurements. Numbers that aren't held. Now, the density of aluminum isn't even truly an exact number because it can always be refined and refined and refined. The density of water isn't an exact number because it's based off of measurements. And it can be further refined and further refined. Now, those that have given us those values have made extremely good measurements and have made hundreds of measurements for those items. Even though they've done it so many times, they are still not considered to be exact. They would be considered what we called an accepted value. It is not an exact number, but it is an accepted as a true value, as the value, as we would have it. So, the term significant figures refers to digits that were measured. When rounding calculated numbers, we need to pay attention to our significant figures. Whether we call them significant figures or significant digits, I think doesn't matter. I think I use significant digits more often than sig figs. So what we want to do is we're not overstating the accuracy of our answers. Is really what kind of starts coming down to is we don't want to overstate things because that's not good. We don't want to make ourselves look better than we already are. It's the filters on Instagram, so to speak. Okay? So you have significant figures can also sometimes, instead of figures, you might hear the term digits. Okay? I sometimes will refer to it as significant digits. Okay, because then it kind of helps that define in the definition part of it. I like significant digits. At one time, I actually considered taking significant digits out of my curriculum for chemistry and or my other science classes until a student came back from college saying, if it wasn't for you and your teaching us significant digits, I would have been lost in college. So therefore, I was like, well, that just justified it. One person saying, I needed that, it helped me. Chances are, they were just the one person to have the confidence to say thank you, or even talk to me afterwards and say thank you. I needed that. That helped. And so therefore, I continued to put it in and have it there. Then we kept adding mastering chemistry. Mastering chemistry requires your answers to be put into the proper number of significant digits. So it just kind of added and solidified what we do in the classroom. So when we have a hypothetical block of wood, on the top one, we have no way of truly knowing where on that 1 meter block this ends. We don't know exactly where that actually ends. We know that there is about halfway. So what we can say with confidence that it's over half, because that's where about half is. We don't know if it's 3/4, which would be about 0.75, which would be over here. Can't say that. So here, it's over half, so we can't really say half. So by saying 0.6 or 60 centimeters is about as good as you can say with the tool that you have. The next image down, well, that helps verify that it's at 60 centimeters. Now, many students would look at that middle one and say, yeah, I say 60 centimeters and move on to my next measurement. How many of you would agree with that? Good, there's some people nodding their head. And honesty is important. But if you look very carefully and very closely, it does go past that 60. And that's where significant measurements come into play. How far past that? Well, we don't know. We can't see. Okay, so guess. That's where you imagine, okay, there's half, there would be quarter, and so it's less than 0.2, but more than 0, so they're guessing 61 centimeters. That 1 is the guess, because we know that it's 0.6. The 1 is that's your first guessed number. Now in the last part, the bottom one, now life becomes even more fun. Zoom in a little bit more on that, and we can see, is it really at that 1? Many students would look at that and say, yeah, it's about 61. Close enough for me. How many of you would say that? Thank you for your honesty. But this is where the little bit of difference of having to make measurements over and over and over again, and actually in some ways forced good measurements upon me because your grade depended upon it, that's not exactly there. Now you get into some more philosophical debates. Is it at that 7 like it says here? Or is it maybe could you maybe say, 60.8? Justifiable, I think. You could even say 60.7, you couldn't say 60.6. It's not quite there. Whether or not that's a 7 or an 8, that's going to come down to personal preference. Do you like to report that unknown 1 as an odd number or an even number? Okay? And whatever you do, you tend to start finding yourself having that personal preference when you're making those measurements. Okay? And that's where the little bit of that error comes in. But if you're making really good measurements, 1 millimeter isn't going to make a massive difference, but it is going to make a difference. And so that's why we have to be consistent and consistently good as much as we possibly can. So making good measurements is extremely important. Here are the rules for significant digits. All non-zero digits are significant, meaning values of 1 through 9 are significant. All non-zero digits are significant. Numbers 1 through 9. Why not 10? It has a 0 in it. Rule number 2, I call the Oreo rule. Okay? Significant digits are like cookies. I would say they're all significant. Whether or not, even if it's a oatmeal raisin cookie, it's still a cookie, right? You might not enjoy it, but if that's the cookie that you get, that's the cookie that you get, and you're going to be like, hey, it's a cookie, right? So the cookie is significant. Now, why do I call it the Oreo? Because the 0 becomes the cream. The cream by itself, it's a debate on whether or not it should be eaten by itself. We're not going to get into that philosophical debate. Instead, the two parts of the Oreo, the cookie, they're significant. And they help make the filling, the icing, significant. Therefore, you're not going to say an Oreo cookie is insignificant. You can eat an Oreo cookie with just the other sides, but then you're just usually looking at it as rule number 1. The middle part, the icing, is significant. It's significant to an Oreo. If you think you're going to get an Oreo and you didn't get the icing part, you're going to be like, hey, what's up? I'm missing something. You're missing something significant. So those zeros do count when they're in between non-zero numbers. Zeros at the beginning of a number are never significant. What do we mean by those? We mean the really small numbers. No matter how big or small they are. Those zeros before that first non-zero digit, they do not count. We have a saying for that. Dot, right, not, left. Why did I write it different? Because the dot right rule is rule number 4. The not left rule is rule number 3. Rule number 3 says not to the left. Those zeros that I have crossed out in red are on what direction of that non-zero digit? They're to the left. They do not count. The ones to the right do count. dot right counts, not left. What do we mean by that? According to rule number 1, the 1 and the 2 count. According to rule number 2, we don't have rule number 2 here. Rule number 3 says not left. Rule number 4 says to the right does. So that example has 4 significant digits. The 1, the 2, and the zeros after the 2. It's like the bottom of your cookie being dipped in chocolate. I'd say it's fairly significant. The rule number 3, they're considered placeholders. They just tell us that the number's really, really, really small. That's about it. In general, the calculated answer can't be more precise than the least precise measurement, meaning you're only as good as your worst measurement. The cliched statement is you're only as good as your worst player, right? Or the chain is only as strong as the weakest link. Your measurements are only as good as your worst measurement. So if you make good measurements all the time, your numbers are going to be good. Unless you just have really good precision and then bad accuracy. So that's where the calculated must be rounded. Always round last. Do all calculations last. That's why having a calculator, I think the TI-84 allows for you to go up and grab numbers easier than the TI-83 did. The TI-83 I don't think does allow that. Keeping those calculated values as that full calculator readout as long as you possibly can is of the utmost importance. So that you just round at the end. And even, there's some rounding things that are the Mastering Chemistry doesn't like us to do, but we do it anyway. But we end up getting the right answer, so it's all important, okay? But round last. That's a big one. As we stated a little bit earlier, when addition and subtraction is performed, answers are rounded to the one with the least significant decimal place, or the one with the least after the decimal place. In multiplying and dividing, it's the least total. In my class, and in a lot of the science classes, we do a lot of multiplying and dividing. Very little do you just do an addition or a subtraction. Usually you do an addition and subtraction on top of a multiplication and division. That's why you wait till the very, very end to do all of that. So, let's do some examples. Let's try it out. So in the first one, we are doing an addition problem. In this addition problem, we can use our calculators. So let's perform the following. Making sure, again, we identify what we're doing. So we can take 43.159 plus 1.23. We plug that into our calculator. We're going to get an answer of 44.389. But is that my answer? And a lot of people would want to say, that that's my answer, and they would answer that, and they would be fine with that. However, my worst measurement is what? It's the 1.23. That has 3 significant digits, which means I need to round right there at the 3. So now it comes into my, how do I round it? Well, 8 is bigger than 5, so you would round up. So my answer then becomes 44.4 grams. Now we're going to subtract. Well, wait a second. That would be wrong. Nobody caught me on it. I'm adding, not multiplying. I don't actually go off of the 3. It's actually the 8. Therefore, because 2 after the decimal place. So it's actually 3.9 grams. Because we're adding, and the rule for adding is the least number after the decimal place. Yeah, see? That's where when we do some of these, you gotta pay attention. I have been known to write the wrong number sometimes, so sometimes on purpose to see if you're sleeping. Not that anyone would sleep in here. So, next one, 48.65 minus, 654 minus 6.210 4. And I get an answer of 42.4436. The one with the least number after is 3. So my answer then needs to be rounded to 3. So I need to round that 3 to a, excellent, 4. And I'm going to write, unfortunately, that wrong. Okay. Milliliters. The next one, 47.134 plus 42.579. Now, sometimes things like this happen. When I put it all together and I do my math, the answer is there. No rounding is required. And the last one, 152.675 plus 12.175. I get an answer of 164.85. But is that my final answer? No. because 5 plus 5 is 10, we still need to add that 0. It is significant. It means something to us. Label grams. Now for some multiplication and division. 3.1415. That sounds like an interesting number. Times 2.5. Get a really long number this time. 7.85375. There's a lot of numbers there we don't need. That one only has 2. Therefore, that number needs to be rounded to be 7.9. But here becomes the confusing part sometimes. Centimeters times centimeters is centimeters squared. Just like in math, x times x is x squared. Same thing works with labels. 1.00, make sure I get the right number of zeros there. 8 times 12.01. Really long number. 12.019608. Holy moly. However, another way of writing it, I need those numbers to stay, which means that 1 gets rounded up to 2. And it's meters squared. 48.010 divided by 4.5. Really long decimal. I'm not writing all of those digits in because they start repeating. 6, 6, 8, 9, because the 8 becomes a repeating number. I can only report 2 significant digits. Now sometimes some people might say 10 point to give that 10 a digit, but what's the first non-zero digit after the decimal place? 6, greater than 5, which means we need to report it as 11 grams per milliliter, because it's grams divided by milliliters. And now the last one, 56.172 divided by 2, we get 28.086. I'm only allowed 1 significant digit. $30 is that significant digit. I don't put a decimal place because if I put a decimal place, then that 0 becomes significant. My label, kilograms per liter.